A second type of problem that you need to be able to do at this point is if you're given a list of acids and the respective Ka values, you should be able to assess the strongest base, the strongest acid, the weakest base, the weakest acid, based on these values. Okay, so for the first one, which of these anions, and the anions would be the conjugate bases, which would be right there, which one of them is the strongest base? So remember, to get the strongest base, we need to look at what was originally the weakest acid. And if you look at the values, the smallest Ka value is this one, which tells you that that's the weakest acid. So its anion is going to be the strongest base. All right, number 2, order these anions according to their decreasing base strength. And then number 3, order the acids according to their increasing acid strength. Okay. So if we look at our K values, let's go with the acids first. The strongest acid, the one that's going to get the number 4, the strongest acid is the one with the biggest Ka value. So that's going to be our 4. And they actually get smaller as you go down from there. So we'll do 4, 3, 2, and 1. If we look at the bases, the strongest base, okay, so decreasing base strength, the one that we're going to start off with, the strongest base is going to come from that weakest acid. Okay, so that'll be our first one. Okay, and they're going to go down from there. Okay, so in this way we can order these different compounds. All right, a third type of problem you need to be able to do is if you're given an H plus concentration, you should be able to calculate the OH minus of this solution. Okay. In order to solve this problem, what you're going to need to do is remember that the H plus concentration, this is from that pH plus box, times the OH minus concentration, is going to give you a Kw value. Okay. Since we know that the H plus concentration is 1.0 times 10 to the minus 2, we can put that number in. And at this point, we're just solving for the OH minus. This should give you a 1.0 times 10 to the minus 12, which you should be able to do in your head because Kw equals 1.0 times 10 to the minus 14th, and 14 minus 2 equals 12. Okay. A fourth type of problem that you need to be able to do is how to calculate the pH for solutions containing strong acids. Now remember, with a strong acid, it's going to dissociate 100%, so you can assume that the given concentration, or the pH of the solution, there is a 100% stoichiometric ratio between the amount of H plus and the amount of HCl that was originally put into the solution. Okay. So in order to do this problem, okay, we really just have to look at that concept. Okay. The solving, if you want to go step by step, what you should be thinking through is sort of the following line of logic. Initially, you should note that the substances used to prepare the solution are actually two types of acids, HCl and H2O. Then you need to be able to list the major species in the solution. This is a pretty critical step. The ground rules must be carefully established. The major species are the components of the solution present in relatively large amounts, and they are written as they actually occur in the solution. Okay, so for this particular problem, what components are present in the 1 molar HCl solution? We have these two. Okay. HCl is a strong acid, and since the original solution contains, or since the solution is going to contain no HCl molecules, because it's going to break up 100% into H plus and Cl minus, we can label this as 1 molar HCl, and we can assume that it's going to produce a 1 molar solution of H plus. So in this way, if we look at this reaction and we compare the HCl with the H2O, we can determine that this is going to be the dominant source of H plus in this solution. Okay. While the H2O does dissociate, the HCl is going to provide the majority of the extra H plus ions that are floating around in the solution. Okay. All right, so basically what we get is if we have a pH, we need the pH of a 1 molar solution. So we know that it was a 1 molar solution of HCl, which tells us that it's also a 1 molar solution of H+, which tells us that our H+ concentration is 1.0 molar. And if we take the pH, if we want the pH, we're going to put it into this formula. Okay. And that's going to tell us that our pH actually equals 0. Okay. Note that a pH of 0 does not necessarily mean that the H+ concentration equals 0. It's just an indication on the scale of 0 through 14 of how strong that acid happens to be. So the big summary point to take away from here is when you're calculating the pH for a solution containing strong acids, you can assume 100% dissociation. You can use a stoichiometric ratio between the original acid and the H+ concentration and use that to determine your H+, which will then be used in this formula to determine the overall pH for the system. All right. The trouble arises when we move on to calculating the pH of a weak acid. Because if you remember, we don't know how much a weak acid is going to dissociate until we perform an equilibrium calculation. Okay? So let's try to calculate the H+ and F- and the pH in percent dissociation in a 1 molar solution of hydrofluoric acid given a Ka value of 7.2 times 10 to the minus 4th. Okay. If you think back to the last chapter, this is a sort of similar problem in that we are given a Ka value, so we're given our K value, and we're given an initial concentration. Okay. So this is somewhat like our type 2 problems from the last chapter. All right, so here's the problem written up so we have a little working space. Okay, so remember, initially you're going to have to list the major species. And our major species for this one are going to be H2O and HF. The acid that's present as HF is going to be written as HF rather than HF or H+ and F- because it's a weak acid and will present primarily as hydrofluoric acid, not as its dissociated ions. Okay? So what we have for our reactions, we've got H2O is going to dissociate into H+ and OH-, a little teeny bit in that autoionization of water. And the hydrofluoric acid is going to dissociate into a little bit into H+ and F-. Okay. So what we're going to do is let's take our equation. We'll take the dominant form of the H+ in this solution, the HF. We'll write its dissociation reaction, the H+ plus the F-. Okay. And let's start off by doing our icebox. So we'll do ICE. All right, so what we assume is that our initial concentration of the HF is that 1 molar that's given in the problem. Okay? And before it gets dissociated, we'll assume we've got a 0 and a 0. Okay? So we're going to have a negative X plus X plus X. So we're going to have 1.00 minus X, X, and X. Okay? So there's our change. If we put this into our law of mass action, we're going to wind up with X squared, because of these two, over 1.00 minus X. Okay? And that is going to equal that Ka value of 7.2 times 10 to the minus 4th. And that's what we were given up here in the problem. Okay? So let me do a little erasing here so I have some board space. If we take this law of mass action and the equation that we have here and solve for our X value, we can actually, in this particular case, make the assumption, okay, which is going to give us an X squared over 1 equals our 7.2 times 10 to the minus 4th. Okay? And this is going to give us an x value of 2.7 times 10 to the minus 2. Okay. Using this, we can calculate that the H plus concentration is, because remember the H plus concentration from the icebox equaled X, so we can assume it equals that. Same thing with the F minus concentration. Okay. And if we want to know the pH, remember that in order to determine pH, pH is going to equal the negative log of the H plus concentration, which we conveniently just calculated. So we can plug that in, and we can then calculate a pH of, let's see, it's going to give us a pH of, well, I'm not finding it, so I'll let you calculate the pH. Then in order to calculate the percent dissociation, you can use the X value that we just calculated to determine the actual, we'll go back to our 1.00 minus X to give us our equilibrium concentration of HF. You can determine the actual dissociation, the percent dissociation from this. Okay, and if you do that, you'll find that the percent dissociation is about 2.7%, which really isn't a lot. Okay. Okay. All right, so that's how you're going to solve one of these more difficult acid-base problems when with a weak acid. You always have to do an icebox. You're always going to need a Ka value. You're always going to have to determine the H plus concentration from the dissociation in order to then calculate the pH. A lot of times the pH is your ultimate goal, but you need to make this calculation first because you have nothing to stick into this equation until you calculate the H plus concentration at equilibrium. Remember, all of these this has to be done at equilibrium.